So this is an interview for David. David, thank you very much for your time. That I recall that I have interviewed you for this special preface 8 years ago, 2010. Time does not run fast, but 8 years has passed. And I think life is long, but it's limited. So we have to enjoy.
Right.
So David, thank you very much for your coming. I'm very look forward to your talk on Friday. And your talk is about epigenetic and aging. So for the people who cannot attend your talk, so would you please explain what does it mean that epigenetic control the aging? yeah. 写真撮って。
はいはい、もしもし。
Oh.
失礼いたします。
Oh, すごい。Female and male is a different color. So this is not a part of the interview.
Yeah. Okay, shall I start?
Yeah, yes, please.
Okay.
Yeah, it's starting already.
Yes. All right. So when we talk about epigenetic aging, we're talking about a new cause of aging. There are two types of information in a cell. One type of information is digital, which is the DNA, and then there's an analog form of information, which is the epigenome.
I see.
And there's a lot of evidence now that the reason we age is a loss of information. Some is in the loss of the genome, but most of the problems is the loss of the analog epigenome. And we know that this is possible because in my lab we can disrupt the epigenome in a mouse, and it ages much more rapidly. And now we're working on ways to reverse that process and reset the epigenome so that cells can read the right genes at the right time. And if we can do that, that truly would be rejuvenation and reversal of aging.
So would you please explain more in detail about your mouse? Yes.
Our mouse, yeah.
Yeah, Motoshi, if you have any questions, you can ask.
Yes. Yeah. So the original findings about the epigenome and its role in aging came from yeast cells, the same yeast that you use to make beer and make bread. And what I was fortunate to co-discover in the 1990s with Leonard Guarente at MIT was that epigenetic factors control the aging process, and you can actually slow down aging. And these epigenetic factors are called sirtuins. But what was most interesting was that during yeast aging, they move. These sirtuin factors, they don't stay where they are on the genome. They move around, and they move in response to damage. So if you damage the genome, such as cutting the genome with an enzyme, or having an X-ray or a cosmic ray,
Right.
The sirtuins will move to the break, and then they try to find their way back to where they came from to reset the gene expression. Unfortunately, we think they don't always find their way home, and over time you have a loss of this epigenetic code on the genome. And a good analogy is a compact disc. When it's new, is nice and easy to read the digital information of the genome, but over time it gets scratched, and then the cell can't read the right genes at the right time, and cells over time, they lose their identity. And we can accelerate this by creating double-strand breaks to create this movement and the shuffling of the epigenetic factors, and make it harder for them to find their way home again. And what we see in this mouse that we made called the ICE mouse, I stands for the inducible changes in the epigenome. If we create cuts in the genome for a few weeks in a young mouse, it will age much more rapidly at about twice the normal rate. And without any mutations, no change to the genome. So this is evidence that it's the epigenetic alterations, not the genetic alterations, that cause aging.
That's a very intriguing theory because based on this, aging can be stopped, but also can be reversed. Why the question arises that when the gene is damaged, and later on the effect come up. So what is the mechanism of this time difference? The onset of the DNA damage, and later on the phenotype.
Yeah. So the reason we think the reason that the effects are seen later on, sometimes months or years later, is that it doesn't all happen at once. That if we distract the chromatin factors, such as the sirtuins, from their normal job, and let's say, for example, 95% or 90% of them find their way back, we've now accelerated that process. But the reason you don't immediately see aging in the animal is that cells still can function okay. But once they reach a threshold with a bit more of the epigenetic changes, then they lose their function to the point where they either become senescent, or they die, or they just don't work efficiently anymore. And with that CD compact disc analogy, we know if you have a little bit of scratches, it's okay. But if you really rub it on the street, it will really be a problem. We think that's what our ice mouse is putting a few early scratches, but then this makes the process accelerate. Now, this may be too much information, but what's interesting is that we think that the changes that we create in the mouse, what they do is they start a positive feedback cycle that accelerates aging. When these changes occur to the epigenome, they actually make it harder for the cell to repair DNA. Okay, so the cycle is we cut the DNA, it gets repaired, but the epigenome changes, and now you don't have very efficient repair. So you get more and more breaks, and not cuts, but breaks, and it just accelerates. So by the time you're old, you have a lot more breaks and a lot more rapid changes.
I see. Roughly speaking, how do you think the epigenome changes contribute? How much % of the aging process?
No one has ever asked me that question.
Because DNA itself definitely contributes.
DNA does, but I think that 95%.
But if epigenetic is 100%, we can live forever, right? So
yes, it is true. But I think that there are some mutations. We still lose some information. We can see those mutations occur in the body, especially in mitochondrial genomes. But our results indicate that the vast majority, 90-95%, is epigenetic.
So you think the 99% is epigenetic. That's wonderful. So then the question arises, how do you interfere? How to intervene this epigenetic? Because if the 90% and if we can control 90%, at least we can live maybe 800 years. Right? Sandra and David, you can live happily for more than 800 years. That's wonderful.
So can you?
Yeah. Yes. Same with that.
She says, 800 yes, happily, not so sure. But I agree, this is the most exciting result in my career, because it means that aging is much more reversible than we thought before. And I thought it would be good if people could live to 120, 130. But now, with these new results, I think that living to 200 will be possible, maybe even more. You can live for 1,000
That's
years.
wonderful. This message is so important to our society, or especially to our conference, to our members.
And so I'm working on methods to reset the epigenome
Right.
by using Yamanaka factors.
Yes.
And there's some some results from other labs as well that indicate you can reset the epigenome to a younger state. So this means one day we will be able to go in and have a treatment. It could be an injection, it could be a pill with a mixture of chemicals to do this, and then we become 10 years younger physically.
That's a very interesting question. That there's a paper that I recalled. If you give the Yamanaka factor for 100%, that you make a cancer, the tumor. But if you give a certain time, period, like 2 days a week, then you can expand your lifespan. So the question arises, of course, the Yamanaka factor, that how much you do or how length you do. So
Yes.
how do you control it? These are very difficult questions.
Yep. So this is the cutting edge of science and aging research right now. In my lab, we have viral vectors that we can infect many cells in the animal when it's old. And we've got these viruses, we can turn them on with a drug, doxycycline, for example, for 1 day, 2 days, 3 days, or 1 day on, 1 day off.
Yeah.
And we are exploring or discovering what is the best regimen, formula to extend lifespan without causing any damage or tumors. And this is really the big question: is you don't want to, how much is enough, but not too much.
I see. So this Yamanaka has 4 factors. Last year I interviewed John Manick in Boston, and we have discussed about this possibility. And she said that these specific factors is too strong because a lot of things is so complex. So she preferred to have a very low dose of rapamycin. You know that. And her claim is that a very low dose rapamycin, we don't know the very complex picture, but can suppress the aging. But if you do like gene editing or the specific factors, we don't know the broadened effect. How do you fight about this concept? It's totally different approach for the anti-aging.
It is. So there are 3 main approaches right now. Now, the old approach that I've been working on as well is to mimic caloric restriction or exercise.
Like NMN.
Exactly.
Or NL.
NMN, resveratrol, rapamycin,
Right.
these turn on the body's natural defenses against aging.
Right.
But they won't reverse aging completely.
But to some
They'll delay
extent,
it. Yes.
that has a value.
Oh, they're very good, but
Yeah.
but they won't get us to 300.
Right. I agree.
They will allow us to live healthy until maybe 120.
Yeah.
The second approach is to delete the senescent cells. And that seems to be promising as well.
Yeah, we have invited the researcher. For
Kirkland?
Yeah,
Jim Kirkland?
Jim Kirkland. Kirkland.
Yeah,
Yes. For this meeting too.
All right, but those first 2 methods are limited. They will give us maybe 10 years more, but not 100 years more.
Right.
In my opinion, the third, which is truly resetting the epigenome, is the most exciting, but also the most dangerous. And I agree with Joan that for now, rapamycin and NMN are the easiest ways to do this.
So number 1 category.
Right. And senolytics are coming along
Number 2
behind.
category. Yes.
But what makes me most excited is the idea of reprogramming the body to be young again, because we think that the information to be young is still in our bodies even when we're old. We just need to teach the body how to read that information correctly again. and that's why we're going after the Yamanaka factors. I also agree with Joan that the 4 Yamanaka factors are too strong. So we are learning in my lab which are the right combinations. We're actually learning that you don't need all 4 factors for it to work.
I see. Wonderful. Yeah, I'm very impressed by the Yamanaka, finding. And the cell can be rejuvenated. Why not the whole body? That I agree. Yeah. So the third category that there's a big, the emerging science of gene editing. So you are a believer of the gene editing. Usually gene editing is for the specific disease like a DNA depletion or some hereditary disease. But you are the believer of gene editing is good for the anti-aging.
I do believe in gene editing, but not just editing, also gene therapy.
Yes.
That adding extra copies of genes that we lose as we get older.
I see.
So in mice we have started replenishing with genetic. Now let me take that back. In mice we've been infecting them with viruses that carry longevity genes to give them, to genetically alter them to make them live longer.
That's wonderful.
What's great about this is we can now intervene in a very old animal and eventually in an old person. Right? The old way of doing it is you make a genetically modified mouse and then you have to wait for 5 years to get the results after you set up these experiments. Now we can get results in just a few months by taking very old mice, 2 years old, and change the genes or add new genes in the lab and get results very quickly. And this is also important because if we're going to treat ourselves, we need something that works late in life. And one experiment that we've just done is we can replace not just one gene, but we've infected with all 7 sirtuin genes in one animal.
Oh, that's exciting.
Yeah. And so far the results look promising.
Oh, wonderful. So you are always challenging the new horizon. So lastly, that I believe that you are interested in translational approach, not only doing the research but also put it into the society. So what at this moment, what is your trend? Because I'm very interested in the translational. Mm-hmm. I'm interested in the innovation, and the innovation happen in this aging field.
Yeah. So I spend a large amount of my time bringing together people who can make use of these discoveries.
Right.
And I'm working on a project that's not publicly known, but I'm happy to tell you.
Is that okay?
Yeah, it's okay.
Okay.
Where there are about 200 people working on different aspects of aging, various causes of aging that we've just discussed. And it probably in the next few months it will become publicly known.
So maybe at the time of this interview, we'll printed that.
Yeah.
Oh, wonderful. So that is not only by the academic university, but by the company based of this. 200 is a big number.
200 PhDs and about 200 patents so far.
Wow.
Yeah.
Wow.
Yeah. Well, I'm learning from you.
It's my great honor. David said that he's learning from me. Wonderful. Thank you very much. So you are so kind. Okay, so thank you very much. It's a bunch of information, and we have learned so much, and I'm very impressed. So I just believe that I have to interview again
In some years.
maybe some month.
Yes, before another 8 years has passed.
Yes. Thank you very much, David.
You're welcome. Thank you.
Thank you. Okay, good, wonderful. Wonderful.